Good morning, everybody. So today's lecture is a bit of an aside. We're going to start doing a lot more calculations coming up for the remainder of the year. Essentially, we do a lot more calculations. Um, and so we need to talk about something that I always talk about a little reluctantly, but hopefully I can give you a little context to understand why we do it. Um, and that's significant figures and keeping track of how many digits we keep in our numbers. Okay. Uh, the main idea here is when we report numbers, we want to tell the truth, the whole truth, and nothing but the truth. Okay. You want to report all the digits that you actually know. You want to report, you don't want to underreport, so you don't want to say fewer digits than you actually know. And you don't want to overreport and say digits that you don't know. So, for instance, I happen to be about 6 feet 2 inches tall. If I say I'm 6 feet, well, that's sort of true, but I'm not telling you the whole truth. If I say I'm 6 feet 2.31564 inches tall, then I'm lying because I'm telling you all these digits that I actually have no idea. Because really, how can you measure someone's height that precisely? So when I tell you my height, I should say I'm 6 feet 2, so that I'm telling you what I know, but no more than I know and no less than I know. Okay? That's the idea behind what we're talking about today. And in your answers that you give on labs or that you give on problem sets or in tests, you're going to want to follow some conventions so that you're not lying, essentially. So our goal is you want to be able to record measurements with the correct number of sig figs, and you want to be able to report results of calculations with the correct number of sig figs. Hopefully this is going to make more sense than just a bunch of rules. You may have had to memorize the rules before, and I want to assure you up front that we're not going to be as rigid with this as they may have been in your previous class. Let's say I have a ruler, this is actually, it should be vertical, but let's say I'm measuring milliliters on the side of a graduated cylinder, and my liquid comes up to the line, the arrow right there. I want everyone, without looking or talking to their neighbors, just record what you think that value is. And there are notes for this in the packet. So. This is called Supplement 9. So there's a little reading in Supplement 9, then there's some practice problems, and then there's these notes. All right, compare with your neighbors. See if you all wrote the same thing. Okay. Iris, what did you write down? 7.6. Did everyone at your table write the same thing? All right, 7.5. Did anyone write something other than those? All right, 7 and 1/4 or 7 and 3/4? 7.7. All right. Now, who's right? The answer is, no one is exactly right. whenever we make a measurement, there's always uncertainty in that last digit. Okay, we always record the digits we know for sure. We know for sure that this is somewhere between 7 and 8. So we know for sure that the first digit is 7. And then as far as the 10th place goes, there's some uncertainty there. Okay, there's always uncertainty in the last digit. Not every reasonable person is going to say the same thing. So what could we do to write this down? Well, we got answers ranging from 7.6 to 7.75, which would be 7 3/4. So 7.5 to 7.7 seems to be more or less the range that they fell in. So how could I write that down? How could I indicate that that's my range? All right, 7.6 plus or minus 0.1 would be the way I could record this with the uncertainty. So here is my best estimate, 7.6. And then this part of my number is called the uncertainty. So we always record all the certain digits plus one estimated digit. So anytime you see a number, you can always assume that the last digit is somewhat uncertain. All right. Now, in different contexts, you might have to do an actual analysis using these uncertainties, and every time you'd have to record exactly what the uncertainty was. We're not going to go that far because it ends up taking an inordinate amount of time for what we do in this course. But what we'll generally assume is when you write a number down, the uncertainty is going to be plus or minus 1 in the last decimal place. And whatever the last digit is, the uncertainty will be plus or minus 1. That's our assumption. Granted, sometimes it's bigger than that. Sometimes it's plus or minus, 2 or plus or minus 3 in the last digit. But we'll make the assumption that it's usually plus or minus 1 in whatever the last digit is. So to keep track of this, we're going to use something we call significant figures. So this term significant figures means something different in this class than it does in other classes. In history, significant figures might look something like those. In English, significant figures might look something like these. And in this class, significant figures are going to look something like this. So these are our significant figures, 1 through 9, and then sometimes 0. We will use the term sig figs for short, just because saying significant figures over and over is just a waste of time. So to keep track of uncertainty, we're going to use this system called significant figures, or sig figs. There are just some conventions that we're going to follow. So today, we're just going to talk about what those conventions are. When you see a number written on a page, you should assume that any non-zero digit is a sig fig. Now here's the rationale for that. If I didn't know the number and it's not a 0, why would I write it down? So we assume that anytime you see a 1 through 9, any of those digits in a number, it is a significant figure. It is a number that is known in that quantity, whatever it is. 0 is sometimes a significant figure. So when it's on the left end of a number, zeros on the left end are always there just to hold the place. So like 0.005. Those zeros on the left-hand side, they're just there to move the decimal place. They're not known values. They're just placeholders. So 0 is never a sig fig when it's on the left end of a number. When it's in the middle of a number, it's always a sig fig. So like if I say the year is 2014, 2014. That 0 in the middle there is a known quantity. It's not like I just put the 0 there to hold the place and I didn't know what the value was. Okay. And then on the right-hand side, that's where it gets a little tricky. Sometimes you put zeros on the right-hand side of a number because you know them, and sometimes you put them there because they're just moving the decimal place. So for instance, if I say to you, all right, you're going to New York. Okay, you go that way about 200 miles. There I'm saying, okay, 200, those two zeros at the end, I don't know what they are. You know, could be 220 miles, could be 195 miles. I don't know. So those zeros at the end are not numbers that I know. They're just numbers that are there to make it 200 instead of 20 or 2,000. They're there to hold the decimal place. But if I say, all right, get on the highway and drive, 200.0 miles, and then take the exit. What am I signaling by saying 200.0? I'm being specific about it. I'm specifying, oh yeah, I know it's exactly 200.0 tenths. So now I'm telling you I know those zero values. So the way we signify that zeros on the right-hand end are significant figures, the way we signify that is by showing the decimal point. So if the decimal point is showing, then you consider all the zeros on the right-hand end sig figs. You say, all right, we know those. If there's no decimal point showing, then you assume the zeros on the right-hand end are just there to hold the place, and we don't actually know them at all. Are there questions? Some sort of special rules that go along with this. If you have a defined number, okay, sometimes you have things, one number is defined in terms of another. Those have an infinite number of sig figs. So there are 12 inches in 1 foot. That's defined as being a perfect value. So really that's 12.00000 out to infinity, or 1 and 1.000. We assume there's an infinite number of sig figs. Okay, because we know that value perfectly. It's not a measured quantity. Same thing when you're doing metric conversions. Like there are 100 centimeters in 1 meter. There's no uncertainty in that. That's exact. When you write things in scientific notation, every digit that you write is a sig fig. So if I write, 3.00 times 10 to the 8th meters per second, every digit over here is a sig fig. These are all sig figs because I wouldn't write them if I didn't know them. Whereas the 10 to the whatever part, that's just there to move the decimal place. So the 10 to the whatever does not affect the number of sig figs in your value. All right, so take these numbers and take a moment, count the sig figs in each one. All right, carry. First number. All right, 4. Because those zeros in the middle are definitely sig figs because they're in the middle. All right. Juliel, how about 2,000? Just 1. Zeros at the right end, just there to hold the place. Mariel, how about the third one? 2. Zeros on the left end, never significant. Okay. And then Robert, 3 in this one because the 0 at the right hand end, since the decimal point is showing, 0 at the right hand end is significant. I wouldn't have written 0.00340 if I didn't actually know that last zero. Eddie, 100.3. This is weird. Why would I write the decimal point? Well, this is our convention, just to say we write the decimal point if we know those zeros. And then the last one, Chris, 6. All right. All right. Question. All right. So the question is in the number 2000, why are those zeros not sig figs, or why do I say I don't know them? So when I write this number 2000, if someone said, well, how much does this cost? And you're like, it's like $2,000. What would a reasonable person assume the cost is? If you say, it's like $2,000. All right, could be somewhere between 1,900 and 2,100. Some people might even have a bigger uncertainty on that. But like this is somewhere between 1,900 and 2,100. So the question is, why is that the case? So in science, we have a convention to say whether we're being precise with those digits or not. And so if I want to be precise with those digits and say, no, it's 2,000, I would write the decimal point at the end. Yeah. But, if I just write 2,000 with no decimal point at the end, I'm assuming it's somewhere between 1,900 and 2,100, which means the hundreds place, I don't really know what it is. It's, really the convention in science is if I write this. So this would be in every day. If I say 2,000, I probably mean between 1,900 and 2,100. But according to our scientific conventions, without listing an error bar there, this means somewhere between 1,000 and 3,000. Like this is what I want you to assume in this class is there's an uncertainty of plus or minus 1 in that one digit. All right, so this means somewhere between maybe somewhere between 1,500 and 2,500, but so there's a big uncertainty if I just write the number 2,000. So the question is, without an uncertainty given, without a plus or minus given, what should we assume? I want you to assume plus or minus 1 in whatever the last sig fig is. And it's not a perfect assumption, but we'll do that just to make our lives easier. So if ever you want to give an answer that's more precise, give an error bar, give an actual plus or minus on your answer. All right. So why do I care about counting the number of sig figs? Well, we just saw in this last example, the number of sig figs really tells us how big the uncertainty is. Okay? If I take the same number, 2,000, and I give it 1 sig fig, that means there's a big uncertainty, right? I said it could be somewhere between 1,000 and 3,000. That's a big uncertainty. If I give it 2 sig figs and I say it's plus or minus 100, now it'd be somewhere between 1,900 and 2,100. Uncertainty is getting smaller relative to the number itself. If you consider, the same measurement 2 centimeters plus or minus 0.1, or 2.00 plus or minus 0.01, or 2.000 plus or minus 0.001. If you consider how big the uncertainty is relative to the number itself, what we call the percent uncertainty, what's going to happen? Well, in this first number, 2.0 plus or minus 0.1, my percent uncertainty is going to be 0.1 divided by 2 times 100%. So what's 0.1 divided by 2 times 100%? 5%. So in that first case, there's 5% uncertainty. Now what if I add a sig fig? Now my percent uncertainty is going to be 0.01 divided by 2 times 100%, which will be 0.5%. And I think you can already see if I calculate the percent uncertainty in this last one, it's 0.001 divided by 2 times 100%. Now it's going to be 0.05%. So the same value, the more sig figs you get, the percent uncertainty gets smaller and smaller. So the question is, by convention, if I'm giving the error bar, do I need to write the zeros after the decimal place? So do I need this 0 right here if I'm giving the error bar? Because doesn't the error bar imply that it's 2.0? Maybe the error bar does imply that, but I'm still going to write it. Yeah. Now, generally, what we're going to do in this class is we're going to write the number without the error bar. All right. So as you add sig figs, percent uncertainty gets smaller and smaller. So the more sig figs you add, the more certain you are about that number. So that's why we care about tracking these, because if you're an engineer and you're going to build a bridge and you want to know, well, how much weight can the bridge hold? And you say, well, it can hold, somewhere between 1,000 and 3,000 cars. All right, well, that's a big error bar. You're going to want to refine your measurements so you get it smaller and smaller. All right. So that's how we count sig figs. That's why we care a little bit about sig figs. Now we need the rules for calculation. So this is where you're going to need your calculators. Here's a multiplication problem. I want you to do this multiplication problem, and I want you to find 3 different results. What's the result of just multiplying the two numbers together? And then considering the error bar, what's the biggest possible result we could get? So to get the biggest possible result, you would take, the first number plus the uncertainty to get the biggest possible first number, second number plus the uncertainty, and then multiply them together. And then do what's the smallest possible result. All right, who's going to feed me the answers? Well, what's just the number? 950.4, all right. 971.98. 928.84. Okay. All right. So I heard a number of groups saying something like this: 950.4 plus or minus 21.56. All right. And what are the units on this result? Centimeters squared. All right. So this would be like calculating the area of something. Does anyone see a flaw in? Because I saw a number of groups representing their answer this way. Does anyone see a flaw in representing the answer that way? All right, so it's kind of annoying to do the 21.56. Now, does it seem weird to say we have this big uncertainty? Like our uncertainty starts in what place value? The tens place. So should we really report an answer of 950.4 with that 0.4? When there's uncertainty in the tens place, do we know the tenths place at all? Not really. So what we're going to do is we're going to say our uncertainty starts in the tens place. So let's round that off to the tens place. So instead of saying 950.4 plus or minus 21.56, let's say, all right, this is somewhere around 950. Plus or minus 20 centimeters squared. Because if we don't know the ones place or the tens place at all, there's no real point in having uncertainty in the ones, saying the uncertainty is 21.56. We don't know those places out there. So we know this is somewhere between 930 and 970. All right, so now our answer, how many sig figs does that have? Well, in our answer, what's the only certain value? The 9 and the 5. There's some uncertainty in the 5, but there's always some uncertainty in our last sig fig. So this has two sig figs, the 9 and the 5. So the question is, couldn't the answer actually be below 930 and above 970? It could be a little bit below 930 or it could be a little bit above 970, but no matter what, it's going to round to 930 or 970. So since we don't know anything about the ones place or the tenths place, we don't really care if it's below 930 in the ones place or the tenths place. So yeah, the answer could be 928.84. That's still 930 as far as we're concerned, because that's as close as we can get. All right, so the answer has two sig figs. We could go through and do a division problem and find the same thing, but what we're going to find every time is that if you consider the error bars and you consider the number of sig figs and the numbers we started with, whichever number we start with that has fewer sig figs is the one that's going to limit our result. So if we look at the numbers we started with, 211.2, how many sig figs there? 4. And 4.5 has 2. When we look at that, we say, all right, the one with 2 sig figs, this is our least precise quantity. And our least precise quantity is going to limit our answer. So our answer can only have 2 sig figs. So the next slide was, let's generalize what we found here. Because this will work out. Anytime you do a calculation with a number with 5 sig figs and 2 sig figs, answer's still only going to have 2. 10 sig figs and 2 sig figs, the answer's still only going to have 2. So I'll skip the division because we're just going to find the same thing. When multiplying or dividing, the result is limited by the least precise quantity. So what you're going to do is count sig figs. In each starting number. Choose the smaller number of sig figs. And only keep that many. You're going to round your answer to that number of sig figs. All right, let's try this once more, but now adding and dividing, because the rule is going to work out slightly differently. Sorry, not adding and dividing, adding or subtracting. So in the next 2 slides, you've got an addition problem and a subtraction problem. So I want you to go through this process for the addition problem and the subtraction problem, because what you find might surprise you a little bit. All right, who wants to feed me numbers? Eddie. Sorry. Point. Oh, 118 point. Oh, yeah. All right. All right, so we get those 3 values. How would we represent the result? All right, 1128 plus or minus 10. I would say that's okay, except if our uncertainty is in the tens place, then I'm probably not going to list something in the ones place. So I would probably change that to 1130 plus or minus 10. And the units on this would be centimeters. All right. All right, the question is, why is the uncertainty in the tens place? Well, when I look at my 3 possible results, they all have the same value in the thousands place and in the hundreds place. The first somewhat uncertain digit is in the tens place. All right. So the question is, I thought we were using this rule. This rule only applies to multiplication and division. For addition and subtraction, we're going to need a new rule. All right, so here, the smallest decimal place that's a sig fig, and the result is the tens place. And with addition and subtraction, you might get confused if you're counting the sig figs, because you might notice we started with numbers that had 2 sig figs and 5 sig figs. And we ended up with an answer that had how many? 3. So when you're adding and subtracting, the number of sig figs in your answer is not what you're tracking. So it's a different set of rules. As we started with 2 and 5, we ended up with 3. What we're tracking really is what decimal place has the uncertainty for adding and subtracting. When you did the subtraction, who's got the numbers for the subtraction? Oh, shoot. That should say subtracting. .0285. .0386. .0184. All right. So I get those 3 values. How would I represent my result now? Where is the uncertainty? In which digit? Carrie? The hundredths. All right. So my uncertainty is in the hundredths, so I got to round my answer to the hundredths place. So this looks like it's about 0.03 plus or minus 0.01. So it's really the hundredths is my smallest decimal place that I can keep. And it turns out that's my only sig fig in my answer. So again, here you're going to get confused if you're going by just counting sig figs, because we started with a number with 5 sig figs and a number with 3 sig figs. And we ended up with a number with just 1 sig fig. So the rule for adding and subtracting can't be about counting the number of sig figs. It's about keeping track of what decimal place you know. Adriana? The question is, would it be wrong to say 0.030 plus or minus 0.010? Yeah, that would be wrong, because it would be saying that we know that thousandths place when we don't. We can only keep one uncertain digit, and in this case, it's the only digit we've got. So for adding and subtracting, again, we are limited by the least precise quantity, but here what you want to do is find the decimal place that's a sig fig in both numbers. And then round your answer to that decimal place. One way that can be helpful to do this, if I take those last numbers as an example, 1.2385 and 1.21. if you write your numbers lined up like this, the digits after 1.21 are question marks. So then when I get my result, when I do my subtraction, I say, oh, what's 5 minus question mark? Question mark. What's 8 minus question mark? Question mark. You know, so I don't know those digits. These are still question marks, so I can't keep them in my answer. So if you line them up with the decimal points in the same place, then you can see where the question marks start, and you have to cut your answer off there. So the question is, can we do it just by looking at the uncertainties? So whichever one has the biggest uncertainty, that becomes the uncertainty in our answer. And the answer is yeah. That definitely works. So in this first one, I had plus or minus 10 centimeters or plus or minus 0.01. Plus or minus 10 became my uncertainty in the answer. And in the second one, plus or minus 0.01 was my bigger uncertainty. That became the uncertainty in the answer. Yep, and that totally works. The reason I'm framing the rule in terms of sig figs is when we do calculations throughout the year, we're very rarely going to put the error bars on, and so we'll just be looking at one number. So if we, if this problem were given later, you wouldn't have the error bar. It would just say 1.2385 minus 1.21. And so in that situation, you want to be able to do it by looking at where the sig figs are. All right, so here's what I'd like you to do. When you do your calculations for problem sets, whatever throughout the year, carry the digits through every step. Don't round after every step of your calculation, because a lot of times, rounding every single step can end up having a big influence on your final answer. At the end, determine, okay, what is the correct number of sig figs? How many sig figs should I do? And then round the result to the correct number of sig figs. Now, the one caveat I'd give here is if you have a problem that has both addition or subtraction and multiplication/division, choose the right number of sig figs after the addition and then do the division. So when you have both of those kinds of steps in a problem, then you're probably going to do two sets of rounding. So an exception. So follow the rules after individual steps. So for example, if you had like 3.5 plus 8.4 divided by 121. if I were doing that problem, order of operations, PEMDAS, so what do I do first? Parentheses. So I'm going to add these two first. So 3.5 plus 8.4 is going to be 11.9. And 11.9, I have 3 sig figs now. So when I do the division, now I'm taking a number with 3 sig figs, dividing my number with 3 sig figs. So now my answer will have 3 sig figs. Sometimes with a problem like this, some people might be tempted to just say, oh, each of these has 2 sig figs, so when I do my division, I'm going to end up with 2. So you got to do the addition first, figure out how many sig figs the answer has, and then do the division. Oh, and I want to actually add in a little slide here. Okay. I don't want the rest of this course to be a course in significant figures. So I don't want you constantly worried about reporting your answer to the right number of sig figs. That's not what we're about here. We're about understanding the chemistry, and then the numbers part is separate. When you really should follow the rules carefully is when doing labs. All right? So anytime you're recording measurements or doing calculations in a lab, I want these rules followed. So in lab, follow the rules carefully because, like I said at the top, this is all about telling the truth, the whole truth, and nothing but the truth. And in our labs, we are usually really limited in how precise our answers are. And I don't want you to be in the habit of lying and saying your answers are more precise than they actually are. So we'll do labs where we measure rates of reaction or where we measure equilibrium constant values. And you may end up with an answer that is only 1 sig fig or maybe 2 at best. I don't want you to report an answer, oh, the K value is 112.35712, when really all you know is the hundreds digit. Okay? So in lab work, I am going to pay close attention. For all other work, so that would be problem sets, tests, quizzes. Three sig figs is a good number. So on the AP test, they generally give you a leeway of plus or minus 1 sig fig in your answers. So if the correct number of sig figs is 2 and you give 3, you get full credit. If the correct number of sig figs is 4 and you give 3, you get full credit. If the correct number of sig figs is 3 and you give 3, you get full credit. Now, I've never seen an answer on the AP test that was not 2, 3, or 4 sig figs as the correct number of sig figs. So guess what? If you get in the habit of always giving all your answers to 3 sig figs, how much credit are you going to get on the AP test for your sig figs? All of it. All right. Now, there is likely to be one question on the AP test that is explicitly about sig figs and the sig figs rules in some lab context, which is why I want you to follow the rules when you're in lab so you get used to them. But on problem sets and tests, I don't want you really thinking about this unless you really feel like, I understand everything, so let me like do the details of the sig figs. But I find that too often people miss the forest for the trees because they're so worried about the sig figs that they're not even thinking about the chemistry. And I do not want that to happen to you. So on tests, I'm not going to penalize you for sig figs errors. And a lot of times we don't even pay attention and we'll give values in a question that only have one sig fig in them. And I know we should do better with that, and we'll try to not do that. But in general, just give your answers to 3 sig figs and everybody's happy. Okay? So we have these 2 sets of rules. Labs, we're really following the rules. Everything else, 3 sig figs is wonderful. And I think that's been a long enough time. So I'll leave it to you to do these calculations for practice if you feel like it, or not. There's some on the problem set.